Hello everyone, this is Trivedi here, and we are starting with the osmosis. So as you remember, this is the third part of the lecture. Okay, so now I'm over here, Naman Trivedi here. Okay, hi, how are you all? Okay, so as you know, we already discussed and we covered two lectures, okay, priorly. In this chapter, this is the third lecture. We'll discuss osmosis over here and plasmolysis. Okay, so we'll start with that. Okay, yeah, just a moment. So whatever we have covered till yesterday, we'll be correlating it over here. Now to understand osmosis, first you should know the basic structure of the plant cell. That plant cell has a cell wall, and then inside the cell wall it has the cell membrane. So it is what we call as cell wall, and over here we have cell membrane. Inside plant cell also has huge vacuole. And vacuole has sap, or what we call as the vacuole sap, inside the cell. Now as you know, the cell wall is porous. The cell wall is porous, and vacuolar sap has solute molecules, other minerals, okay, and it decides the solute potential of the cell. It decides the solute potential of the cells. So if you talk about the vacuole, the membrane of the vacuole is what we call as tonoplast. We have discussed the same thing in the chapter of cell. Tonoplast is also a phospholipid bilayer. Just same as mentioned in your textbook in that chapter. Okay, so it has inside, it has what we call as sap, or what we call as vacuolar sap. Okay, and this determines the permeability of this. Okay, and the cell membrane will determine the movement of molecules which will happen inside and outside the cell. Movement of molecules which will happen inside and outside the cell, that is mainly determined by this tonoplast membrane as well as the cell membrane. Now what is osmosis? So osmosis is a term which we use to define the water diffusion, of water across semi-permeable or selective permeable membrane. So osmosis mainly depends on two things: pressure gradient and concentration gradient. So the net direction and the rate of osmosis is dependent always on pressure gradient and concentration gradient. So water will always diffuse from a region of higher concentration to lower concentration. So it can be said as from a region of higher chemical potential to lower chemical potential. And the movement will continue till equilibrium is established, so let's say it has higher water potential, it has higher concentration of water, then water will move from A to B, and the movement will continue till both will have the similar or equal concentration of the water. In other words, water will always move from higher water potential to lower water potential. Also remember, more the solute, less the water potential. Less the solute, more H2O molecules, more water potential. Okay. Now we'll just take a simple experiment which is mentioned over here of the potato osmometer, which you might have done in your school in the practical. So let's say we have a beaker. I'm drawing a beaker over here. Okay. Now I'll just do it again. Okay. Let's say we have a beaker. Inside this beaker, I am putting this potato. I have peeled all the contents of the potato out, and here I have filled it with this sugar solution, and I am marking it over here. Okay, so here we have sugar solution. Now outside in this region there is water. Outside there is water. There is this water, is the blue color part which you see. There is water is there. Okay, so outside has this has higher side W, okay, and this has lower side W. So the water movement will happen from this part to this part. So water will diffuse in the potato tuber from outside to the inside, and you'll observe that this level which was marked over here will reach on the next day. It will be enhanced, or it will be reached to this layer. Why? Because water has entered, so this level will go up. Water has entered, so this level will go up. The entry of water will make this level go up. So it's a simple potato osmometer experiment which you might have done in your school in the practicals. So what it shows over here, at this region we had high side W, so water has moved from this region to the inside. Here we have more solute because sugar solution was there. Here only there was H2O, so the H2O will move from here to here or to the inside, and this is what we call as the potato osmometer. So that is what they have explained to you in that is what they have explained in this paragraph. Okay, now they have given a wonderful activity in the figure number 11.3. So remember that they have given you two systems or two chambers. They have given you two systems, or what we call as two chambers. Okay, they have given you two systems or two chambers. Both these chambers are separated by what we call as a semi-permeable membrane. So one is chamber A, other is chamber B. All these particles are solute particles. Over here also you can see these are all, the pink dots are all solute. Now they ask some questions. You have to apply water potential logic, osmosis definition, and then you have to answer. Mainly it is based on water potential. It is very important. A lot of teachers will not teach you this. A lot of books have given wrong answer. A lot of books have not mentioned this, but we will discuss. Very easy and very interesting. So now the first question is, which chamber has lower water potential? Now the first question is, which chamber has lower water potential? So as you know, the chamber A and B, A has less solute. Okay, I'll just a moment, I'll just zoom in a bit. Excuse me. So there are two chambers A and B, and the question is which has lower water potential. Okay, so you can also keep your textbook with you when you want to see this. So let's say B has more solute, A has less solute, so H2O will be more in A. So the answer is B will have less water potential, and the water will move from A to B. The water will move from A to B. So A has high side W. A has high side W. So B has lower. B has lower side W. Remember that. Now we'll take the second question. The second question is, which chamber has lower solute potential? Second question is, which chamber has lower solute potential? This is what we are discussing, the second question, or the B. Now if you know, yesterday we have discussed this sentence, and if you have read or if you have gone through my notes, you might have known that this paragraph, if you remember, over here it was mentioned that solute potential will always be negative on dissolution of a solute. So more the solute, as you can see in this sentence, more the solute molecules, lower the psi s. More the solute molecules, lower the psi s. More the solute molecules, lower the psi s. I'll just zoom in a bit, okay, so that you can easily see it. So over here, the more solute molecules, more negative the psi s. So in that relation, B has more solute, so B has lower solute potential. B has psi s will be low for the B. Okay, remember that. In which direction osmosis will occur? It's very easy. Here there is more water in the A, B has more solute, so less water, so osmosis will always from high water to low water concentration, or higher water potential from to the lower water. So it is very easy. The answer for third is, it will be always be from A to B. will be always from A to B. So for this C of question, the answer is A to B. Which has higher solute potential? Which has higher solute potential? So now try to think it. When we talk about the higher solute potential, it denotes the amount of solute in it. So as you know, in this diagram, A has less solute, so more solute can be added over there, so the answer will be A. So it has more potential, to potentially accommodate more solute. So higher solute potential will be of the A, because B already has more solute, so you cannot add more solute, so the solute potential of B will be less than that of A. So A has higher solute potential. Next question, at equilibrium which will have lower water potential? At equilibrium which will have lower water potential? Equilibrium will not never be low or high, it will always be equal. When both will have equal water potential, we call it as equilibrium. Or in other words, when psi WA is equal to psi WB, the equilibrium will be established. So none of the chamber will have higher water potential. For E, the answer will be none. The next question they have asked about the pressure potential, or psi where they have denoted, because in the G question number G they have mentioned psi W, so it is water potential. So here I am taking in the F question as the pressure. So pressure, they have mentioned that there are two chambers, one is minus 1000 Pascal, another is minus 2000 Pascal. Okay, just write it again. They have given us two chambers, one is minus 1000, other is minus 2000. Okay, so which will have higher psi W? So over here you have to think that, as you know, the pure water as high as 0, and it is as per the usual mathematical sign convention in this case, because they denoted in the F question pressure potential. So this will have the higher psi W. Why? Because as you know, mathematically minus 1000 is bigger than minus 2000, so this will be higher. Last question, that is the G. Now they have mentioned that we have psi W of one is 0.1, another is 0.2. Now you know we take 0 as the highest psi W, so which will have the higher water potential? So 0.1 is higher water potential, and that's why the water movement they have asked. If this is semi-permeable membrane, water movement will always be from 0.1 to 0.2. Because pure water is highest and that is 0, so it will always be from 0.1 to 0.2, because this one has mainly higher water potential as compared to 0.2, considering 0 has the maximum water potential. So in this condition you can say that 0 is bigger than 0.1 and 0.1 is bigger than 0.2 for this F question, the G question. Okay, so that's all from this questions. It is very much important, kindly go through it. Now next part, they have given you an experiment to demonstrate the osmosis. In this diagram, as you can see, you might have studied the same experiment in the lower standard. Okay, now it's very easy experiment. You see this thistle funnel, you can see this thistle funnel. So this thistle funnel has a, inside that there is sucrose solution. This region outside in the beaker there is water, and over here if you see this part they have tied this circle. They have tied this semi-permeable membrane, which you can also get from the eggshell by dissolving it in a hydrochloric acid. That you can read from this paragraph. Okay, so I'm not going in, it's very easy. Now after some time you observe that the water level which was marked, let's say in the thistle funnel, okay, let us assume this as a, just a moment, okay, let us assume this as a thistle funnel, okay. Now the level which is marked over here of the sucrose solution, if it will be placed in water, after some time observe that this level will reach to this stage, this level will reach to it will increase. So this increase is because of the water coming from the outside, or this part, as you can see. So what it shows, it shows that water is diffusing, across the membrane, as you can see by these arrows, okay. And whatever pressure you have to apply from this part to stop this movement can be termed as the osmotic pressure, So this is what the increase they are showing over here. It was there, now it is increased to this stage because of the entry of this water onto the inside through the semi-permeable membrane. So coming back, this paragraph is very much important. I'm zooming in a bit so that you can easily go through it. So basically, whatever external pressure you apply from the upper part, so that to stop the water from moving, okay, this pressure is stop the diffusion of the water from outside to the inside, is termed as the osmotic pressure. It depends on solute concentration. More the solute concentration, more the pressure required. Now also we have something called as osmotic potential, okay. So osmotic potential is always negative, pressure is always positive. So you should remember it as, if we take osmotic potential and pressure, then it is positive. Osmotic potential is always negative. Both are same, equal and opposite. So potential refers that the potential of this system, which is on the inside, to take up more water from the outside, while the pressure refers as the pressure required from here to stop this diffusion, the pressure required to stop. It refers to osmotic pressure, and this refers to osmotic potential. Okay, so both are equal and opposite with the negative sign convention. Remember this sentence especially. Okay, so from this part you should know definition of osmosis, okay, as well as the role of the semi-permeable membrane and the water potential. Now next part is about plasmolysis. Just hold on a moment, let me have some water, then we'll start with the plasmolysis. Okay, so plasmolysis can be correlated to something, or can be attributed to something which is nothing but the osmosis and the movement. So here they will be taking three solutions: isotonic, hypertonic and hypertonic. So it's all depends on which solution you are putting your plant cell in. If the inside of the plant cell and the outside has same concentration, we call them as isotonic. So the cytoplasm over here and the outside solution has same concentration, we call it isotonic. If outside is more dilute, we call it hypertonic. If outside is more concentrated, we call it hypertonic. Usually cells will swell in what we call as hypertonic, whereas it will shrink in what we call as the hypertonic. So cells will shrink in hypertonic, will swell in hypertonic. How? Swelling means water will enter inside and there will be enlargement. Shrinking means water will be going outside, so there will be shrinking or decrease in the size. Now the most important part, the definition of plasmolysis. So it occurs when water will be moved out of the cells, and this only happens when you put the cell in the hypotonic solution. So I'll just explain with respect to this diagram. So you have put the cell in, let's say, hypotonic solution. Okay, you have put the cell in the hypotonic solution, which is outside over here. So water will move from this region to the inside. So water will move from this region to the inside. Okay, or what will happen? Now try to think something. Just a moment. Yeah, see, this part has more H2O and this has mainly less H2O. This is more concentrated. So where the water movement will happen? So water will move from inside of the cell to the outside. Water will move from inside of the cell to the outside. As you can see the zero. Okay, as you can see the zero. So water will move from the outside. And hence, if you look at this structure, you can see there is this shrinked cell is there. The protoplast has shrinked. So you can see that the cell membrane, okay, along with the cell, the protoplasm has been shrinked because water is moving out of the cell in the case. So it is always, plasmolysis is always in relation to the what we call as hypotonic. Now second condition is when we have a flaccid cell, when we'll have a flaccid cell. Now try to understand, flaccidity is always obtained, flaccidity is always obtained when it is placed in isotonic, when it is placed in isotonic. Why? In the case of the isotonic solution, both inside and outside will have similar sort of concentration, so there is no H2O diffusion or movement, and that is what said to maintain the cell in as it is condition, termed as the flaccid cell. So it is for isotonic, so it is for isotonic. Finally we have what we call as the basically the turgid cell. Finally what we have is the turgid cell. Now if you talk about the turgid cell, then the only remaining part which we have now is this one, or turgid cell. So when this turgidity will happen, when the water from the outside, when the water from the outside, and just zoom in a bit, when the water from the outside will enter inside it. So it will happen when we have placed this in what you call as the, we first discussed about the hypertonic, isotonic. Okay, so when water will enter from the outside, when outside we have hypotonic. Okay, when outside we have hypotonic solution, so outside we have more H2O, so water will move from outside to inside, as you can see over here, and that is where we will get the turgid cell. That is where we will get the turgid cell. So try to understand. Okay, plasmolysis is observed when cell is placed in the hypertonic solution. When the cell is placed in the hypertonic, isotonic you will have flaccid cell, hypertonic you will have turgid cell. So remember all of this because it has been asked frequently. Okay, so here as you can see water is moving out. Okay, here as you can see nothing happens because both is same. Here you can see water is moving in. Okay, so remember and read all these paragraphs, it is highly important. Okay, all whatever I explained in the diagram is the same they have given in this paragraph. It is very much important for question. Also you should know that when the water diffuses in the cell, okay, it will create a pressure against the wall. It will, when the water diffuses against the cell, just a moment. Okay, let's say there is, this is the cell. and water is diffusing inside the cell, so it will create a pressure against the wall. This pressure is called as turgor pressure. This pressure is called as turgor pressure. Turgor pressure will always be a pressure against the wall. Turgor pressure will always be a pressure against the wall. So remember this. Turgor pressure will be against the pressure against the wall, which they have mentioned you in this sentence. Okay, which I have also discussed yesterday in the water potential. So it is the pressure exerted by protoplast because of entry of water, and this is called as pressure potential or psi p. And that's why this turgidity of the cell maintains the cell shape and structure, so the plant cell will not rupture because of it. Okay, also they ask one more example about the psi p of the flaccid cell. So psi p of the flaccid cell is always equal to 0. Now to understand this, you need to understand about the part which I have taught you yesterday. So just a moment. Okay, just a moment. So if you open out my notes, you can understand that in that I have explained to you about the this thing. Okay, this part, as you can see. So you can see turgor pressure is always against the wall, then we have wall pressure, and then we have OP. From that we talked about the DPD. Okay, then from that we discussed the DPD. I also shared my notes in the group, you can go through it. So you should know when the cell is fully turgid, DPD is 0. Now in the flaccid case, psi p is always equal to 0. Why psi p is equal to 0? Because flaccidity is obtained when it is in isotonic, and isotonic it's all equal, so there is no net movement, so this psi p is always 0. Okay, so that's why in relation to that, when the wall pressure is negative, dpd is equal to op plus the wall pressure. When flaccid cell is placed in the pure water, it is always op minus dp, as you know. A decrease in osmotic pressure and cell shape will happen. Also, it is the same term, dpd is the same term which we use for water potential. You should know the wall pressure is exerted by the wall. Okay, it is the wp. Osmotic pressure is because of the osmotic entry of the water, and Tp is because of water which is entered inside the cell. This is always equal and opposite. So always we consider this as these conditions which I have explained yesterday. Okay, so go with these calculations, try to solve some questions. It is very much important. Okay, it is very much important. So from today's topic, plasmolysis and osmosis is important, especially plasmolysis. You should know when the cell will get flaccid, turgid, or when it will get plasmolyzed. That's all. This is Naman Trivedi signing off. If you have any doubts, put in comments, or you can directly message me, and do let me know how you are enjoying these lectures or not, because I'd seen there's been no response from you guys. Okay, so obviously give me some response so you can understand and you can improve it, or I can do some improvement in this condition. Take care, stay safe. Thank you guys.